Hello everyone, welcome to the algebraic graph theory seminar. Today we have Tom Wong from Creighton University. He will tell us about the quantum search. Tom, please.
Thank you. Thank you all for joining. I want to start off just by wishing everyone a happy World Quantum Day. So today's April 14th, and every year scientists around the world celebrate quantum mechanics, quantum physics, quantum technologies. And so, giving a talk about quantum walks seems like a great way to celebrate this with you all. So I'll be talking about work with one of my undergraduate students, Molly McLaughlin. And so she is a senior double major physics and math. And we'll be talking about work that was actually just published last month. So this is quite recent in the physics journal, Physical Review A. You should have access to it through your university, but if you don't, it's also on the archive. And so this is supported by the National Science Foundation through the Equate collaboration, which is like a 20 PI giant collaboration in the state of Nebraska, where we are. So yeah, you'll be able to read lots more about what I'll be sharing about today. Okay, so to introduce this, I want to start with a continuous time random walk. And so let's say we have a graph, and this example just has four vertices. And a random walk on this, so classical random walk, is going to be given by a probability distribution over these four vertices. So there's some probability at each of the four vertices that we're labeling 1, 2, 3, and 4. This is going to evolve in continuous time by a differential equation. So what we get is that on the left, we see that how this probability distribution changes is given by some constant gamma, which is the jumping rate, times L, which is the discrete Laplacian. And so I'm going to be using the physics sign standard, which is to do A minus D versus D minus A, that many of you might prefer. And so A is the adjacency matrix that has a 1 if two vertices are adjacent and 0 otherwise. And D is the degree matrix. And so I think in this group, this is all things that you guys know actually better than I do. And so if you subtract those, again, I'm using the sign convention that you have A minus D, then we get the graph Laplacian. And one of the important things I want to highlight with this is that the columns of this sum to 0, and this is necessary so that the total probability is conserved. So that way it stays a total probability of 1. Okay, so how do we tweak this to make this a quantum walk? Well, instead of a probability distribution over the vertices, we have a bunch of amplitudes, or like numbers, just like complex numbers. So we're going to call those C1, C2, C3, and C4 at each of the vertices. And in physics, we typically write a vector using this ket notation, where you have a vertical bar on the left and like a big right angle. It kind of looks like a big greater than sign. So this is a column vector that we call a ket. So this column vector is called psi. And the way we get a probability from this quantum state vector is we take the norm square of each amplitude. So if I take the norm square of this first amplitude or this first coefficient, then that's the probability that when you measure the position of the walker that you'll find it at vertex 1. Take the norm square of the second amplitude, that's the probability that you'll find it at vertex 2, and the same thing at vertices 3 and 4. Now this quantum state vector is going to evolve by a slightly different equation. It's going to evolve by Schrodinger's equation, which is the fundamental equation of quantum mechanics. And if there's any physicists here, we're working in units where h bar Planck's constant is equal to 1. And so Schrodinger's equation looks like this, where you have an I times the time derivative of your state vector. And that's going to be governed by this matrix H, which is the Hamiltonian. And the Hamiltonian can be interpreted in different ways. So from a computer science or mathematics perspective, this Hamiltonian really just needs to do two things. It needs to be Hermitian or self-adjoint, meaning that it equals its conjugate transpose. And that's going to ensure that the total probability stays equal to 1. And the other thing is that it needs to respect this graph that we have. And so from a computer science or math perspective, any Hamiltonian that is Hermitian and respects the structure or connectivity of this graph is a valid quantum walk. But from a physics perspective, this operator isn't arbitrary. It actually characterizes the total energy of the system. And so there's something physical behind this. And so with the type of quantum walks I'll be sharing about today, I'll revisit this at the end of the talk to give some physics motivation for why the signless Laplacian might be a reasonable Hamiltonian to choose for a quantum walk. Um, Okay, so there are three types of quantum walks that I'll be referring to in this talk. So the first two are ones that many of you have seen before. They're very common. The first one is the Laplacian quantum walk, where the Hamiltonian is equal to the negative gamma, where gamma again is the jumping rate, times the discrete Laplacian that we had already. The other type of quantum walk that is also very common is the adjacency quantum walk, and this is just minus gamma, the jumping rate, times the adjacency matrix alone. So we're dropping that diagonal degree matrix. And so these two types of quantum walks appear in tons of investigations, tons of papers. Many people in this audience have done research on these types of quantum walks. But at one of these types of meetings, I think it was in Canada, hosted by like Chris and others. I was presenting some work on quantum search algorithms, and I can't remember who they asked if I had ever looked at an algorithm involving the signless Laplacian, and that is what kind of gave birth to this research, which is to look at the signless Laplacian quantum walk. And so when it was raised to me, I was like, what's the signless Laplacian? I'm a physicist. I'm not a graph theorist. And you guys all graciously explained to me that it's just A plus D instead of A minus D. And so, from that computer science or math perspective, this is a valid Laplacian to investigate. It respects the structure of the graph. It's a Hermitian, so the total probability stays equal to 1. And as part of this talk and part of the research that Molly and I did together, we looked at, if there's some physical motivation for this type of quantum walk as well. And so with this signless Laplacian quantum walk, there's only been a handful of investigations. I think I only counted like two or three, and they all involve state transfer. And so Molly and I looked at a search algorithm using this. And so basically there's these three different types of quantum walks, and we might ask, how do these three types of quantum walks act the same, or how do they act differently? And so this work, we're going to ask, algorithmically, how does this signless Laplacian differ from the first two that have been investigated much more thoroughly? And then is there some physical motivation for it? And so we're going to talk about the search algorithm first, and then we'll end with the physics motivation. All right, so we need a problem to investigate in order to compare these three types of quantum walks. So we want a graph that is analyzable, that has lots of symmetry, where even for me as a physicist, I can prove something about it. And so, well, what graph kind of has the most symmetry, is the easiest to analyze for me? Well, I usually think of the complete graph. But as you all know, the complete graph actually affects the exact same basically all three of the quantum walks I just talked about on the previous slide, they all walk in the same way on regular graphs, including on the complete graph. So this is not a good problem if I want to compare these three types of quantum walks. And the reason for this is because that diagonal degree matrix is going to be proportional to the identity matrix. And any multiple of the identity matrix in the Hamiltonian can be dropped because there's a couple ways to think about it. One way mathematically is that it constitutes a global phase. And when you take the norm square of all the amplitudes to find the probabilities, that global phase ends up not doing anything. Another way to think about it from the physics perspective with the Hamiltonian being energy is that you can choose where zero energy is. And so dropping this constitutes just re-zeroing where your zero energy is. And so that is an arbitrary thing you can do. So we want a graph that's not regular. It needs to be irregular and still be analyzable, have lots of symmetry. And so a reasonable one is the complete bipartite graph. And so here is a complete bipartite graph. We're going to take N1 and N2 to be the number of vertices in each partite set. And we might ask, how does a quantum walk behave on this? But a previous result from actually some of you on here, I think Tino is on here, I saw, um, is that if you just do a quantum walk, that's not a search algorithm or anything like that, then the standard Laplacian and the signless Laplacian are actually equivalent on the complete bipartite graph. And so if you want to have a difference between these types of quantum walks, you can't just do uh, a walk on the complete bipartite graph. You need to add something to it. And the part that we added is spatial search. And so we're marking some vertices, say K1 vertices in the left set and K2 vertices in the right set, indicated by those double circles. And the idea is that we don't know which vertices are marked, and we're trying to find one of them. And what we know from some prior research that I did with collaborators is that at least for the standard Laplacian and the adjacency matrix, that they search this complete bipartite graph differently. And so, a natural question is whether the signless Laplacian also searches this differently, or if it searches similarly to the other two. And so because we're looking at a search problem, this could constitute the first algorithmic investigation of the signless Laplacian quantum walk. Because like I mentioned earlier, that at least investigations that I know of previously pertain to state transfer. And so let's go ahead and introduce this idea of the spatial search algorithm. So what I have here is a map of Latvia, which is where I did my first postdoc back in 2014 to 2016. And so let's say you're here outside of the University of Latvia. So this is one of the buildings. And let's say you're looking for a cafe. And so if you're not familiar with Latvia, or if you don't have your phone on you, you might just figure that, this is Europe. If you just wander around, you're bound to find coffee. And so, one algorithm that you can take in order to find a coffee shop is to just do a random walk. And so from that street corner, you have three different options. You can go up and left, up and right, or down and right. And so you randomly pick a direction, and let's say you go up and to the left. You end up there. You ask, is your coffee here? Nope. You can take another step of your random walk. Again, you have three options. You can go up and left, up and right, or you can go back the way you came, down and right. You randomly pick a direction. Say you go up to the right. You ask, is there a cafe here? No. You pick another random direction out of those three. Say you go up and to the left. You end up there. You ask, is there a coffee shop here? No. Now you have, I think, 5 different options. You pick one at random. Say you go down to the left. You ask, is there a coffee shop here? And yes, there is. So you have found your coffee. So this is a classical random walk. If we do this as a quantum walk, then your state evolves in a superposition or a linear combination of like options. And so from this street corner that you're starting off at, instead of moving just in one direction, you can move in a linear combination of all 3 directions. So you end up in those 3 locations. If you take another step, then you walk along all of those options, which will take you there. And what you see is that there is some amplitude, which you can take the norm square of to get a probability. So there's some probability that if you measure the position of the walker, that you'll find it here at this location where there is a cafe. And the idea is that you want to tune your algorithm so that the probability of finding the particle or the walker at a cafe is high. And so, of course, we want to know how fast this takes, and it's going to be different depending on what graph you look at. And then for us, we're looking at the complete bipartite graph. Okay, so how do we turn this quantum walk into a search algorithm? What we do is we add what's called an oracle, which is what we query to ask, like, is your coffee here or not? And so what it looks like in the Hamiltonian is we have our quantum walk piece from before. So if it's a standard Laplacian quantum walk, we have minus gamma L, and we tack on this additional piece, which is the outer product of each marked vertex. So I mentioned that this ket is how we write a column vector. This thing that's the flip version of it, we call it a bra, and that is a row vector version of it. So it's the conjugate transpose of it. So this is a column vector times a row vector. So this is an outer product or a matrix So we add this Hamiltonian oracle to it, and that's how we mark our vertex while we're walking. So we can compare these three types of quantum walks. We have our standard Laplacian quantum walk with a search oracle. We have the adjacency quantum walk with the search oracle, and we have the signless Laplacian quantum walk with the search oracle. And each of these are just going to evolve by Schrodinger's equation from some initial state. And the initial state we're going to use is actually going to be the principal eigenvector of each of these walk operators of the Laplacian, the adjacency matrix, or the signless Laplacian. The reason for that is because these initial states are the ones that cause the success probability to reach 1. And so what this looks like for each of these quantum walks is the following. So for the standard Laplacian quantum walk, the principal eigenvector is just the uniform state. So it's a uniform superposition over all n vertices. And for many search algorithms, this is the state that you start with. For the adjacency quantum walk, it's going to look like this. So the initial amplitude that you have on the left vertices is going to be 1 over the square root of 2n1, where again, n1 is the number of vertices you have in that left set. And then in the right set, the initial amplitude is 1 over the square root of 2n2, where again, n2 is the number of vertices you have in the right set. And then for the signless Laplacian quantum walk, Molly and I showed that the state you want to start in is this one, where the initial amplitude of for the left vertices is the square root of n2 over n1, where capital N by itself is the total number of vertices. And then the initial amplitude for the vertices on the right are similar. You just swap n1 and n2. In our paper, Molly and I talk about what happens if you start in this uniform state for all 3 quantum walks, and basically your success probability won't reach 1 for the adjacency quantum walk or for the signless Laplacian quantum walk. But I'm not going to really talk about that today. Although if you want to ask about it, you can. Okay, so let's look at how the search algorithm evolves on the. So again, it evolves by Schrodinger's equation from whatever initial state I just showed you on the previous slide. And so since the Hamiltonian is time independent, then this differential equation solution is just that the state at time t is given by e to the minus I ht times your initial state. And then the goal is that when you measure the location of your walker, that you find it at a marked vertex. One of the things is that the jumping rate gamma plays a really important role in how successful this algorithm is. And so I'm going to give you an example. So let's say we search on the complete bipartite graph where we have 512 vertices on the left set, 256 vertices on the right set. In the left set, 3 of them are marked, and in the right set, 5 of them are marked. And we're going to look at how the success probability evolves as a function of time for different values of the jumping rate gamma. And so when gamma is, say, 1,000ths, what happens is that your success probability, it starts off small from that initial state. And you can see that it grows just a tiny bit, but it stays pretty small the entire time that you run this algorithm. If you make gamma a little bit bigger, so instead of 1,000ths, let's say it's 15,000ths, so like that, we see that the success probability, again, it starts off at the same low value. And then now it ends up growing to a much bigger value here. So now it's about a probability of like 15% if you were to measure at this location that you would find the particle at a marked vertex. If you make gamma bigger still, let's say gamma is 2,000ths, and you can see now that at this time about 35, that the success probability is nearly 1. So if you were to measure the position of the walker at this time, then with probability nearly 1, you would find it at a marked vertex. So meaning that you found a marked vertex and you solved this search problem. If we make gamma bigger still, let's say 0.0025, we can see that it's actually not performing as well as it did when it was this green option, 0.002. If we make gamma bigger still, it got better again. So why don't we keep making gamma bigger? But why don't we clear this graph? It's getting a little bit busy. Let's say we make gamma a little bit bigger still, when the gamma is 0.0035. Now the success probability is quite high. It's about, I don't know, 85% at that peak. If we make gamma bigger still, oh, now it's almost 1, which is great. Make gamma bigger still. Oh, it's getting worse again, and worse again, and worse again. And so what we see is that with the signless Laplacian quantum walk, there's two values of gamma that make your success probability near 1. And so Molly and I were able to prove this analytically. And to give you the results, I'm going to introduce some notation, which comes from the fact that all of these algorithms evolve on this complete bipartite graph in a four-dimensional subspace. And so basically, there's only 4 types of vertices. So all of the marked vertices in the left set that I've now labeled as A and have colored red, these all evolve in exactly the same way. So with the same amplitudes. Similarly, the marked vertices in the right set that I've labeled B and colored blue, these all evolve in exactly the same way. Here on the left, all of the unmarked vertices labeled C and colored yellow, these all evolve the same way. And all of these D vertices on the right, these unmarked vertices, these all evolve in exactly the same way as well. And so again, we can then simplify this problem where evolving in an n-dimensional space, we evolve in a 4-dimensional subspace. And that 4-dimensional subspace is spanned by uniform superpositions over all of the A vertices, over all of the B vertices, over all of the C vertices, and all of the D vertices. And so we'll just call those A, B, C, and D to denote the marked vertices in the left set, the marked vertices in the right set, the unmarked vertices in the left set, and the unmarked vertices in the right set. And so this allows us to simplify all of the math and actually solve what goes on. And so I will go ahead and give you the result. And so for the signless Laplacian quantum walk, again, there are 2 different jumping rates that cause the success probability to reach 1. The first critical jumping rate where this occurs is when the jumping rate is 1 over the number of vertices in the left set. And Molly and I were able to prove analytically that the initial state, which again is the principal eigenvector of the signless Laplacian, that this evolves to the marked vertices in the left set, which is a success probability of 1. And that the time that this takes is pi over 2 times the square root of the number of vertices in the left set times the total number of vertices divided by the number of marked vertices in the left set times the number of vertices in the right set. And so we're going to call this TQA. So this is the time that it takes for the signless Laplacian to find a marked vertex in the left set. And again, we're calling those vertices A. With the signless Laplacian, we have the other critical jumping rate, which is 1 over n2. And then the principal eigenvector of the signless Laplacian will evolve to the marked vertices in the right set, which we're calling B. The time that takes is given by this, which is the same thing just by symmetry. If you swap n1 and n2 and k1 and k2, you get this result. And we'll call that TQB. And just to compare this to the other quantum walks that came from previous research that I did with some collaborators back in 2016, with the normal standard Laplacian, there's actually also 2 jumping rates. So when the jumping rate is 1 over n2, then this regular Laplacian quantum walk evolves to the marked vertices in the left set. And so what we see is that the jumping rate is actually reversed. So with the signless Laplacian, gamma being 1 over n2 evolves to B, whereas with the standard Laplacian, when gamma is 1 over n2, it evolves to A. So that's a difference. And the amount of time it takes is different as well. So if the standard Laplacian quantum walk finds the marked vertices in the left set in time pi over 2 times the square root of the total number of vertices divided by k1. Which is the number of marked vertices in the left set. The other critical jumping rate for the standard Laplacian is 1 over n1. So again, it's the same jumping rates as the signless Laplacian, but the behavior is switched. So whereas one searches for A, the other searches for B, and vice versa. So in this case, the standard Laplacian evolves to the B vertices, the marked vertices in the right set. And the runtime is going to be now pi over 2 times the square root of n over k2. And we'll call that TLB. For this adjacency quantum walk, it's actually different from both of these in that it only has one critical jumping rate. So which should be 1 over the square root of n1, n2. So there's only one value of gamma that causes the success probability to reach 1. And it evolves from its principal eigenvector to actually a combination of the marked vertices in the left and right sets. And so we get this particular combination. And the amount of time it takes is different from all the other ones as well. The runtime looks like that, and we'll call that TA. Okay, so this is like the main algorithmic result. We also have the physics result, which is what's the physical motivation for the signless Laplacian. And you can see again that the evolution can be different depending on the jumping rate, and the runtimes are all different. And so, okay. So we have these 5 different runtimes that we've called TQA, TQB, TLA, TLB, and TA. And we might want to compare these to see like which one is the fastest under different conditions. And so let's go ahead and compare these 5 runtimes now. And so what I'm going to assume for this comparison is I'm going to assume that the N1 is much bigger than N2. So there's a lot more vertices in the left set than the right set. You can also do the opposite assumption and just switch the roles of N1 and N2 and K1 and K2. And so let's go ahead and look at the case when N1 is 1024, N2 is 256. So again, there's a lot more vertices in the left set than the right set. Say there's 5 marked vertices in the right set. And what we're going to do is we're going to compare these 5 runtimes as the number of vertices in the left set scales. So let's go ahead and start with this first one. So with the Signless Laplacian quantum walk, it's able to find the A vertices, the marked vertices in the left set in this runtime. And if we plot this runtime now, we get this curve. So we see that as K1 gets bigger, this runtime gets smaller, so it goes faster, which makes sense, right? So K1 is in the bottom here. So this should scale as 1 over the square root of K1. So that's what this curve is. Let's look at TQB. If we plot this one here, we get a constant. And again, if you look here, this doesn't have K1 in it, so it should be a constant. So here again, this is the runtime. So smaller is faster or is better. So, over here, this is faster than this black curve. But over here, this black curve is now faster than this red curve. So, okay, let's plot the next one. So with a standard Laplacian, finding the marked vertices in the left set, this should also scale as 1 over the square root of K1, but with a different factor. And so that curve looks like that. And so we see that this standard Laplacian searches more quickly for a marked vertex in the left set than the signless Laplacian does, which is this black curve. Now for the 4th runtime, this one should also be a constant. It looks like that. And finally, with the adjacency quantum walk, this one's a little bit more complicated, but it does have a K1 in it, so it should not be a constant, and it should get smaller as K1 gets bigger. That one looks like that orange curve. And so what we see is that in this regime to the left, when K1 is small, so when there's not many marked vertices in the left set, that the Signless Laplacian quantum walk is actually the fastest out of all 5 of these. So again, in this region, the Signless Laplacian is the fastest. And then when K1 reaches this point, then we have a transition where now the adjacency quantum walk is the fastest. Doing a little bit of math, that transition occurs when K1 is equal to K2 times N1 times the difference of N1 and N2 divided by N2 times the total number of vertices. So now in this intermediate range of K1, the adjacency quantum walk is the fastest. And then at this point, we have another transition given by this expression when K1 is equal to K2 N1 N over N2 times the difference in the number of vertices. And now for a larger number of marked vertices in the left set, we see that the Laplacian quantum walk is now the fastest. And so basically, for these 3 types of quantum walks, each of them is faster under different conditions. And I guess what's interesting for us with our investigation of the signless Laplacian is that there is a regime where the signless Laplacian is the fastest. And so, given this, it kind of raises the question of whether or not the signless Laplacian quantum walk is faster than the other two for other problems. And so just to give an example of this, let's look at the case when K1 is equal to, let's say, 2. Excuse me. And so this puts us squarely in the regime where TQB should be the fastest, then TA, then TLB, and then TLA, and then TQA should be the slowest. So let's go ahead and plot how each of these evolves just to confirm that. So TQA, I'll just go in order. TQA is going to look like this. This one is the slowest one. So the success probability starts off really small, and it takes up to time about 80 to reach the success probability of 1. TQB, this one very quickly finds a marked vertex. It only takes time, I don't know, what's that? 13, 12, 13, to reach a success probability of 1. This one was the fastest one. TLA, that one evolves like this. So it reaches 1 at around time 40. The TLB, that's this one here, reaches 1 at about time 25. And then the adjacency quantum walk reaches 1 at about time 15. And so this agrees with what we just had in the previous plot. And so again, the takeaway of this is that the signless Laplacian can be faster than the other types of quantum walks. And so this third type of quantum walk might be something that's interesting to continue studying. All right, so that's the first part of my talk, which is on the algorithmic part. The rest now is going to be on the physical motivation of this. And so it turns out that this physical motivation of spin networks, which can motivate the first two types of quantum walks, the standard Laplacian and the adjacency quantum walk, that there are physical systems where these can also motivate the signless Laplacian quantum walk. And so we're going to dive into how that works and what those systems might look like. And so we're going to look at a network of spin 1/2 particles in physics speak, or you can think of it as a network of qubits. Or another way to think of it is that since quantum spins act as little magnets, you can just imagine that you have a bunch of magnets on this graph. And so you can see that they're currently pointing all sorts of different ways, but the idea is that if you have an edge connecting two vertices, then these two magnets are going to interact, and they might want to exert forces on each other and point in the same direction. And so these two magnets are going to be wanting to align. These two magnets might want to align. These two are going to want to align, and these two are going to want to align. And so there's different quantum mechanical models that we have for these networks of quantum magnets. So one way is with this XY model with ferromagnetic interactions. What ferromagnetic means is that these want to align in the same direction. And in this case, they want to align in the X and Y directions in the same direction. And so what the Hamiltonian for this system looks like can look like something like this. So the Hamiltonian is minus some parameter. I'm going to let that be our jumping rate gamma because it's going to appear in the quantum walk in a little bit, divided by 2. And then what we're doing is we're summing over all pairs of adjacent vertices. So we're summing over this pair of vertices 1 and 2 that are adjacent, vertices 2 and 3, vertices 2 and 4, and vertices 3 and 4. So we're summing over all of the pairs of adjacent vertices. And for each of those pairs, we have in our Hamiltonian these Pauli matrices acting on each vertex. And so these Pauli matrices, or what we might call them in physics, in quantum computing, these are quantum gates. These are like the X and Y quantum gates. And what they do is they characterize the X and Y components of spin, which is a type of angular momentum. And so again, for this graph, we have 4 different edges. So we're going to sum over 4 different pairs of vertices. So we have vertices 1 and 2, which will give us the poly X and Y matrices for 1 and 2. We have vertices 2 and 3 that are adjacent, vertices 2 and 4 that are adjacent, and vertices 3 and 4 that are adjacent. So the entire Hamiltonian for this particular graph might look like this. All right. Another model for these spin networks is called the XYZ model. Excuse me. And if we again have ferromagnetic interactions, meaning that these little magnets want to point in the same direction, then it'll look very similar to what we have before, except now we have these quantum gates that are these Z operations or these poly Z matrices. And so what we could do, excuse me, is we can split this up into two sums where we have the exact same XY model Hamiltonian that we had on the previous slide, plus this additional term that has these ZZ interactions. And so this is another model that people study for these physical systems. Excuse me. And now, so basically these first two are ones that many people have looked at before for these types of quantum walks. We'll see that the first one basically gives rise to the adjacency quantum walk. The second one gives rise to the standard Laplacian quantum walk. And so, I asked Dr. Jonathan Rubel, one of my physics colleagues here, I was like, hey, are there any of these models where this Z interaction has the opposite sign of the other interaction? So where we have ferromagnetic interactions in X and Y and antiferromagnetic interactions in Z, meaning that in the Z direction, the magnets want to point in the opposite direction from each other. And it turns out that he was a great person to ask because he actually worked on these systems for his PhD thesis. And so he actually gave me some examples of this. And so again, the only thing we're changing in this third model is now this Z component has the opposite sign. And so if we split off the XY sum from the ZZ sum, what we see is that this just has a plus sign now instead of a minus sign. And so he gave me a couple of examples of actual physical systems where you have layers where within layers, in the X and Y direction, you have ferromagnetic interactions where the spins want to align. But then in between layers, in the Z direction, you have antiferromagnetic interactions. And so what we'll see is that by changing the sign, this will give rise to the signless Laplacian quantum walk. Basically, this left term is the adjacency matrix. This right term is the degree matrix. So we're switching the sign of the degree matrix to go from the Laplacian to the signless Laplacian. And so I'm going to go ahead and work through with you all how that works. So the way it works is we have to work in what's called the single excitation subspace. And so what we're going to look at is we're going to look at the eigenstates of the poly Z operator. And in physics, we typically write these as spin up and spin down using arrows. In quantum computing, we typically just call these the 0 and 1 state. I mentioned that these spins act as qubits, so these are just your 0 and 1 for your qubits. And so these are eigenstates or eigenvectors of the poly Z matrix, and 0 has eigenvalue 1, and 1 has eigenvalue -1. And so what that means is that this 0 state has a higher energy, because I mentioned that Hamiltonian relates to energy. So you think of it as its energy is 1, versus the 1 state or spin down that has an energy of -1. So it has lower energy. So it's unexcited. And so when we talk about the single excitation subspace, we're going to have a single 0 state that's higher energy, and then the rest will be in this 1 state that's lower energy. We can also see how the poly X and Y matrices act on these eigenstates of Z. So what X does is it turns 0 into 1 and 1 into 0. So in quantum computing, X is your NOT gate. So it turns 0 into 1 and 1 into 0. Y turns 0 into I times 1, and it turns 1 into minus I times 0. So it also turns 0 into 1 and 1 into 0, but with a complex phase here. All right. So again, we're going to be working in a single excitation subspace. So for the graph we have here, I'm going to pick Z to be pointing upward just so I can draw this more easily. We could have this single excitation at vertex 1, could be one example. So here we have this magnet pointing up along Z, so that magnet is in the 0 state. And then the remaining 3 magnets are all pointing down in the 1 state. So we see how we have a single excitation, a single 0, and the rest of them are in 1. And so we can write this state now as 0, 1, 1, 1. And that's a perfectly fine way to write this state. Or another way to write this is that vertex 1 has the excitation. So we can just write this as 1. Another possibility is that this excitation could be at vertex 2. So here, this is in the 0 state. And at vertices 1, 3, and 4, these magnets are all flipped upside down. So these are all in the 1 state. And we could write this as 1, 0, 1, 1. So that's one way we can write this. And a shorthand way to write this is that the excitation is at vertex 2. So we can just write this as a 2. Next one, the excitation could be at vertex 3. So the magnet's pointing up there. It's in the 0 state. All the other ones, their magnets are pointing down. They're in the 1 state. So we could write this state as 1, 1, 0, 1, like that. Or as shorthand, we could just write this as 3 because that 0 is at vertex 3. And finally, the excitation could be, oops, sorry, the animation broke, can be at 0. And then we have 1s everywhere else. And so we can write this as 1, 1, 1, 0. And as shorthand, we can just write this as 4. Okay, so basically, we now have a way of writing. So if you think of this as a quantum walk now, where the 0 is jumping around from one vertex to the other, and we're keeping track of where that 0 is. Okay, so let's see how that XXYY Hamiltonian, how this acts in this single excitation subspace. And we're going to look at pairs of adjacent vertices. So we'll see, how does XXYY act on, say, 0, 0? Well, in the single excitation subspace, you can't have an excitation at 2 vertices, so this just doesn't occur. What can occur is you can have 0 at one vertex and then 1 at another vertex. So what XX will do to this is it'll turn 0 into 1 and 1 into 0. So this 0, 1 will turn into a 1, 0. And then YY will turn 0 into 1 times I, and it'll turn 1 into 0 times minus I. And then I times minus I will give us 1. So what we get is 1, 0 plus 1, 0. So we get 2 times 1, 0. What's another option we can have? Well, we can have that the excitation's at the right location and it's not at the left. So how does XXYY act on 1, 0? Well, XX will turn 1, 0 into 0, 1, and YY will also turn 1, 0 into 0, 1 because the minus I times I will just give me a positive 1. So this is also 2 times 1, 0. Oh, sorry, this should be 2 times 0, 1. Sorry, that's a typo there. And then how does it act on 1, 1? So if the excitation is not at either vertex, then XX turns 1, 1 into 0, 0, and YY turns 1, 1 into minus I times 0 and minus I times 1. And minus I times minus I is negative 1. So we get 0, 0 minus 0, 0, which is just 0. And so how does this work out on this graph? Well, this XXYY then, if we have the excitation at 1, what's going to happen is that it's going to jump over to 2 with a factor of 2. If the excitation is at 2, it's going to jump to all of its neighbors. It's going to jump to 1 and jump to 3 and jump to 4 with coefficients 1, 2, and with coefficients 2, 2, and 2. If the excitation is at 3, then this Hamiltonian will cause it to jump to its neighbors to 2 and 4 with coefficients 2 and 2. And if the excitation is at 4, it's going to jump to 2 and 3 with coefficients 2 and 2. And so we can write this operator now as a matrix. And it's going to look like this. And this is exactly 2 times the adjacency matrix. And so the Hamiltonian that we started off with, this is going to become proportional to the adjacency matrix. Excuse me. What about ZZ? Well, let's go ahead and look at the 4 different options. So ZZ can't act on 0, 0 in the single excitation subspace because we can't have 2 excitations. The way it acts on 0, 1 is it flips the sign because z turns 0 into 0 and it turns 1 into -1. It's also going to flip the sign of 1, 0. And then it does nothing to 1, 1 because it will turn it into -1 times -1 and the minus signs will cancel out. And so in this example, let's see how this acts where the excitation is at vertex 1. So remember, ZZ, we're summing over all pairs of adjacent vertices. So we have a pair being vertices 1 and 2 are adjacent, vertices 2 and 3 are adjacent, vertices 2 and 4 are adjacent, and vertices 3 and 4 are adjacent. And if the excitation is at vertex 1, what's going to happen is that this Z1, Z2 is going to give us a minus sign. So we get a -1 because of these options here. And then from this fourth option here, Z2, Z2, Z3, Z2, Z4, and Z3, Z4 will give us positive ones. So what we get is -1, +1, +1, +1. If the excitation is at vertex 2, then this Z1, Z2, and this Z2 and Z3 because it has a Z2, and this Z2 and Z4 because it has a Z2, all three of these are going to give us a -1 because the excitation is at vertex 2. So we're going to get a -1 3 times. And then here, between vertices 3 and 4, there's no excitation there, so you get a +1. When the excitation is at vertex 3, it's not at vertices 1 and 2, so we get a 1. It is at vertex 3, so Z2, Z3 is going to give us a -1. It's not at vertices 2 and 4, so we get a +1. And it is at 3, so we get a -1. So what we get is that we get 1, -1, +1, -1. And finally, if the excitation is at vertex 4, then we get a -1 from these last two terms and a +1 from these first two terms. And so what we see is that we have 4 different terms here that would be +1, except if the excitation is at one of the vertices, then that +1 is going to flip to a -1. And so in general, what we get is that we get however many terms that's equal to the number of edges. So here there's 4 edges. And then depending on how many neighbors a vertex has, that many ones will turn into -1s, which is a difference of -2. So we can add a -2 times the degree of vertex I. And so if we were to just write this sum of Zi, Zj as an operator, we get that this is the number of edges times the identity matrix -2 times the degree matrix. And since we can drop any multiple of the identity matrix, this is just proportional to the degree matrix. So this is -2 times d. And so our 3 Hamiltonians that we're looking at, they all become these types of quantum walks. So when we just had x, x, y, y, since this sum is 2 times adjacency matrix, the factors of 2 cancel out, and we get that this is minus gamma times the adjacency matrix. So this is the adjacency quantum walk. For the XYZ model, this first term again is twice the adjacency matrix, and this term now is minus twice the degree matrix. So we substitute those in, we get minus gamma times the adjacency matrix plus gamma times the degree matrix. Factoring out minus gamma, we get minus gamma times A minus D, which is the minus gamma times the standard Laplacian. So this is our Laplacian quantum walk. And then this third model that we're introducing in this paper, we're flipping the sign of this term. So we end up getting A plus D. So this is minus gamma times Q. And so to conclude, Molly and I have conducted what we believe is the first algorithmic investigation of the signless Laplacian quantum walk. And we did that by looking at search on the complete bipartite graph. What we found is that the signless Laplacian is the fastest of the 3 quantum walks in some parameter regimes. And this raises again whether or not the signless Laplacian is faster at other problems. And then we show that this arises in spin networks, assuming that you have ferromagnetic interactions in 2 directions and antiferromagnetic interactions in the 3rd direction, and that we're working in a single excitation subspace. And I will end my talk there. Thank you.
Thank you, Tom, for the nice talk. Do we have questions, Tom?
Can I ask one question?
Yeah, for sure.
Yeah, can you hear me? Yeah, I hope.
Yes, yes, I can hear you.
Yeah. Okay. So why complete bipartite graphs? Why not any other biregular, semi-regular bipartite graphs? Because you have given a reason for not regularity avoiding, but why not
Mhm.
we consider semi-regular bipartite graphs?
So it's because of the very first bullet point in our list of things that we wanted. We wanted something that's very easy to analyze. And the complete bipartite graph makes it so that the system evolves in a four-dimensional subspace. So basically, when we had to prove all the runtimes and everything, it allowed us to write the Hamiltonian as a 4 by 4 matrix. And then we just had to find the eigenvalues and eigenvectors of a 4 by 4 matrix. So basically, we picked this graph because it's easy to analyze, because if you're gonna start off with a problem, you kind of start with the easiest case first, and then you can then explore more complicated problems if there's motivation to do so. And what we're seeing is that there is motivation to do so, because the Signless Laplacian quantum walk can be faster than the other two.
My that's really nice one, but my focus is like is any other biregular bipartite graph will be of significance in the physical sense.
Hmm? Yeah, definitely. I mean, if you want to be the most physical, then exploring this on like a lattice or something like that might be much more physically implementable. But again, the idea with this is like, if you're doing the first investigation of something, you should start with what is the easiest,
Yeah,
and then that gives you
that's
motivation to
understood.
explore systems that are more physically realizable.
Yeah, that's understandably right. Thank you. It was a very nice talk. Yeah.
Thank you.
Earlier you have the table of for use Laplacian matrix, Signless Laplacian or adjacency matrix with different initial state and running time.
Oh, uh, this one.
Yeah.
Yeah.
Do they all approach the state with probability 1 or?
Yeah, so these are asymptotic results. So for large N1 and N2, then the system approaches, A, B, or that combination of A and B.
So the probability is high, but might not be 1.
It asymptotically approaches 1. So
Okay.
yeah.
So does the ratio of N1 and 2 influence the I don't know the approach? No, I don't know. I guess how
Is your question how quickly they
Hello.
converge, or like how quickly they approach 1?
Yeah, but you have the running time. I guess that's the part.
Yeah, I mean, I guess you can compare them a little bit by looking at this plot here. So these are all with the same parameters, and it looks like this black curve is a little bit less than 1, more that so than some of the other curves. So maybe that one is converging a little bit more slowly, or sorry, to 1. But that one's also the slowest one, so we don't really care, right? We
Yeah.
care more about what happens with this fastest one.
Yeah.
Yeah.
So if you have a biregular bipartite graph that is not complete, I know you don't have these kind of four grouping. You would probably
Yeah.
a more complicated version. But do you expect something similar to happen in terms of the runtime and the success rate?
I mean, I don't know if anyone's explored that for any of these 3 types of quantum walks. So, I mean, my guess would be that all of them are going to act differently.
Okay.
I'm just guessing, though.
I see.
Tom, can I ask a question?
Sure.
Thanks for the talk, by the way. Following up on Ada's point, do you think sparsity kills in this case?
You mean if it's more sparse, will
Yes.
these walks behave more similarly or more different? Is that what you're asking?
More slower.
Oh, will it search more slowly? So I guess this is a general question. This doesn't pertain to trying to compare these types of quantum walks. I mean, we know that at some limit, sparsity will kill, right?
Yes.
I mean, this is kind of like, as you know, like some work that I did a while back was looking at the graph connectivity and how that, can that provide some intuition for whether or not a graph supports fast quantum search? And, what we showed is that the answer is ultimately no, but there is still some level of intuition where that's kind of true, or some limit where it's true. And so, I don't think we have a full enough theory to really know, like, because I think it's going to vary depending on like what type of sparsity you're talking about.
Right.
This is the one where you have the simplex of the complete graphs, right?
Yeah.
Yeah. So what?
Yeah, so that one's an example where the connectivity is high, but search is slow, at least if it's unweighted.
Right,
Yeah.
I'm just kind of playing with that picture now. Like, what if you have two groups of complete subgraphs of two sizes, right? And then you can have the connection between those two groups, like almost like a biregular bipartite graph, and then do a spatial search and then see what happens.
Yeah.
This is just for fun.
Yeah.
Yeah. Okay. Thanks for the talk. I have to go. I have a student coming in for office hour.
Yeah, you're welcome.
Yeah,
I've got a meeting to get to as well. So
Okay.
thank you all.
Yeah. Thanks, Tom.
Thank you, Tom.
Yep, take care.
You too.